Hi guys, welcome to Matsi with me, Miss Resi, your teacher for today. So today we're gonna discuss about scientific notation and significant figures. In physics, we deal with some numbers that are very small and other that are very large. It can cumbersome to write numbers in conventional decimal notation. In scientific notation, any number is written as a number between 1 and 10 times integer power of 10. Thus, the radius of the Earth, approximately 6,380,000 meters at the equator, can be written as 6.38 times 10 raised to 6 meters. The radius of the hydrogen atom is 0.0000000000053 meters, can be written as 5.3 times 10 raised to negative 11 meters. Scientific notation eliminates the need to write zeros to locate the decimal point correctly. In science, a measurement of the result of a calculation must indicate the precision to which the number is known. The precision of a device used to measure something is limited by the finest division on the scale. Using a meter stick with millimeter divisions as the smallest separation, we can measure a length to a precise number of millimeters, and we can estimate a fraction of a millimeter between two divisions. If the meter stick has centimeter divisions as the smallest separations, we measure a precise number of centimeters and estimate the fractions of a centimeter that remains. The most basic way to indicate the precision of a quantity is to write it with the correct number of significant figures. The significant figures are all the digits that are known accurately plus the one estimated digit. If we say that the distance from here to state line is 12 kilometers, that does not mean we know the distance to be exactly 12 kilometers. Rather, the distance is 12 kilometers to the nearest kilometer. If instead we said that the distance is 12.0 kilometers, that would indicate that we know the distance to the nearest tenth of a kilometer. More significant figures indicate a greater degree of precision. There are rules in identifying significant figures. Number 1. Non-zero digits are always significant. Number 2. Final or ending zeros written to the right of the decimal point are significant. Number 3. Zeros written to the right of the decimal point for the purpose of spacing the decimal point are not significant. Number 4. Zeros written to the left of the decimal point may be significant, or they may only be there to space the decimal point. For example, 200 centimeters could have 1, 2, or 3 significant figures. It's not clear whether the distance was measured to the nearest 1 centimeter, to the nearest 10 centimeter, or to the nearest 100 centimeter. On the other hand, 200.0 centimeters has 4 significant figures. Rewriting the number of scientific notation is one way to remove the ambiguity. Number 5. Zeros written between significant figures are significant. Significant figures in calculations. Number 1. When two or more quantities are added or subtracted, the result is as precise as the least precise of the quantities. If the quantities are written in scientific notation with different powers of 10, first rewrite them with the same power of 10. After adding and subtracting, round the result, keeping only as many decimal places as are significant in all of the quantities that were added or subtracted. Number 2. When quantities are multiplied or divided, the result has the same number of significant figures as the quantity with the smallest number of significant figures. 3. In a series of calculations, rounding to the correct number of significant figures should be done only at the end, not at each step. Rounding at each step would increase the chance that round-off error could snowball or adversely affect the accuracy of the final answer. It's a good idea to keep at least 2 extra significant figures in calculations, then round at the end. When an integer or a fraction of integers is used in an equation, the precision of the result is not affected by the integer or the fraction. The number of significant figures is limited only by the measured values in the problem. The fraction 1/2 in an equation is exact. It does not reduce the number of significant figures to 1. In an equation such as c is equal to 2 pi r for the circumference of the circle of radius r, the factors 2 and pi are exact. We use as many digits for pi as we need to maintain the precision of the other quantities. Sometimes a problem may be too complicated to solve precisely, or information may be missing that would be necessary for a precise calculation. In such a case, an order of magnitude solution is the best we can do. By order of magnitude, we mean roughly what power of 10. An order of magnitude calculation is done to at most one significant figure. Even when a more precise solution is feasible, it is often a good idea to start with a quick back-of-the-envelope estimate. A calculation so short that it could easily fit on the back of an envelope. Why? Because we can often make a good guess about the correct order of magnitude of the answer to a problem, even before we start solving the problem. If the answer comes out with a different order of magnitude, we go back and search for an error. Suppose a problem concerns a vase that is knocked off a 4th-story window ledge. We can guess by experience the order of magnitude of the time it takes the vase to hit the ground. It might be 1 second or 2 seconds, but we are certain that it is not 1,000 seconds or 0.00001 seconds. Dimensional analysis. Dimensions are basic types of units such as time, length, and mass. Warning: the word dimension has several other meanings, such as in 3-dimensional space or the dimension of the soccer field. Many different units of length exist: meters, inches, miles, nautical miles, fathoms, leagues, astronomical units, angstroms, and cubits, just to name a few. All have dimension of length, and each can be converted into any other. We can add, subtract, or equate quantities only if they have the same dimensions, although they may not necessarily be given in the same units. It is possible to add 3 meters to 2 inches after converting units, but it is not possible to add 3 meters to 2 kilograms. To analyze dimensions, treat them as algebraic quantities, just as we did in the units. Usually, capital letter M, L, and T are used to stand for mass, length, and time dimensions, respectively. Equivalently, we can use the SI-based units kg for mass, M for length, and S for time. Applying dimensional analysis. Dimensional analysis is good for more than just checking equations. In some cases, we can completely solve a problem up to a dimensionless factor like 1 over 2 pi or square root of 3. Using dimensional analysis, to do this, first, list all the relevant quantities on which the answer might depend. Then, determine what combination of them have the same dimensions as the answer for which we are looking. If only one such combination exists, then we have the answer, except for a possible dimensionless multiplicative constant. Problem-solving techniques. No single method can be used to solve every physics problem. Even for a particular problem, there may be more than one correct way to approach the solution. Problem-solving techniques are skills that must be practiced to be learned. Think of the problem as a puzzle to be solved. Only in the easiest problem is the solution method immediately apparent. When you do not know the entire path to a solution, see where you can get by using the given information. Find whatever you can. Exploration of this sort may lead to a solution by suggesting a path that had not been considered. Be willing to take chances. You may even find the challenge enjoyable. When having some difficulty, it helps to work with a classmate or two. One way to clarify your thoughts is to put them into words. After you have solved a problem, try to explain it to a friend. If you can explain the problem's solution, you really do understand it. Both of you will benefit. But do not rely too much on help from others. The goal is to each of you to develop your own problem-solving skills.